Okay, hello. So we are going to be taking some notes today. And at this point in time, everybody should have out a line sheet of paper. And also, whoever is helping me out today, if my sub has not yet, if my sub has not yet passed out the protractors, if you could take a second to pause the video and get those passed out. We're going to need those today. And so we might have some pausing here and there throughout the video, and that's okay. All right, so paper should be out, should have our protractors in front of us. The title of these notes and the purpose of these notes today is to look at a couple phenomenon that is involved with light, our visible light portion of the spectrum, as well as the law of reflection. So go ahead and title your notes Light and Law of Reflection. So we're going to look at how does light behave when it hits a flat surface. And this is going to be a nice introduction to mirrors, flat plane mirrors, so how images are made into mirrors. And you'll be getting a little more of an investigation of that on Monday or Tuesday when I see you next. And so we'll be able to see the ties of the law of reflection on those days here. So our Wednesday work, we kind of dove in a little bit about some of the theories on what light or all forms of radiation are. Up to this point in time, we've talked about the wave theory of light. So the wave theory of light, or as well as any form of radiation, we're focusing on light, but this is really for all forms of radiation on the electromagnetic spectrum, says that light, or again, just really any form of radiation. And as you can imagine, we should be writing this down if we're not at this point in time. So light is a transverse wave. So light exists as a wave and it in fact exists as a transverse wave. So a transverse wave, that's a wave that vibrates perpendicular to motion. Now we have some observations that supports or that proves, that shows that light indeed exists as a wave. So one of those first observations, behaviors that we can see is the fact that we can polarize light. Polarization, you might be more familiar with if you have polarized sunglasses. All polarization is the filtering of any form of radiation. In this case, the filtering of light. And so you have a medium in which light cannot pass through. And so what polarization does is if you orientate that medium in a particular direction, it blocks the light waves from passing through in that particular direction. So I have a couple polarizers here. I have some arrows to show their orientation. So it's too small to see, but this film here is polarized vertically, up and down. So we can see if when I put this underneath the overhead projector, it's darker, so it's blocking some light. So in fact, it's blocking the light waves that are going this way, up and down. But it is allowing some light to pass through. So that's why you can still see what's underneath. Now if I put another polarizer on top, and I have it in the same direction, I can still see So these are both going vertically up and down. So it's still just blocking the light that's going up and down. I can still see what's underneath, which tells me that some light is passing through. So the light now is being blocked vertically, so only light that's moving horizontally is passed. So now if I take this polarizer and I switched it horizontally so that it blocks light now both in the vertical and the horizontal direction. So now we block all forms of light, or all orientations of light. So now no light can pass through the polarizer. So it's completely blocking all of it. Waving my hand underneath, and as you can see, you can't see now. Here again, I have them layered up on top of each other. So on the portion where we don't have the polarizer, that's horizontal, so we can still see underneath because some light's passing through. But on the horizontal side, and it's completely black, so we can't see any light passing through. If I move this slow enough, you can kind of see the transition from where we block the light out to where now, oops, some light is passing through. So we get back to about half of the light waves passing through. So polarization, the fact that we can filter light, is a support of wave theory, an observation that supports that theory. Another observation that we have of light that goes with wave behavior is the interference patterns that can be made from light. So as we know from our previous wave units, interference is when two waves meet and combine to form a new wave. If their amplitudes are in the same direction, they build and we have constructive interference. And if they're in opposite directions, they cancel each other out and we have destructive interference. So the interference of light can be observed when a beam of light hits something that's really tiny. That causes the light to bend, and as a result of that bending, it causes the waves to build and to cancel each other out. So I have a laser pointer here, and I have what I like to call a little photo gate here with some really tiny materials. I have some fishing line, I have a piece of wire here that I'm going to shine the light on here in a second. So without the little tiny materials blocking the beam of light, when I just hit the laser pointer, we have light leaving the laser pointer, just passing on to the paper here. I'm going to turn these lights off just to make it a little easier to see. All right, so here's my laser pointer here. So now I'm going to put my gate, or my small piece of wire here, in front of the laser pointer. Now when I do that, and if I hit it just right here, right over the top, I see a beam of light, so a line that goes on either side. Let's see if we get that with any of these other ones here. It might just be one. There we go. There's another one. All right, and one more. So that beam of light that goes sideways from all directions I guess maybe not all directions, just horizontally there. So that was what we call an interference pattern. So it's a little hard to see from the screen there, but if we were able to get up close, we would have the beam of red light coming from my laser pointer here. And then on either side of that, that line that you would see was actually not a solid line. So if we could get our faces up real close to it, we're going to actually do a lab like this here in about a week. you'll see that you would see that the light actually has some gaps to it. So it's a line that has these really tiny little gaps that goes right around that beam of light there. And so these are interference patterns. So areas where the light is present would be constructive interference. So the two waves are meeting and building. And areas where there would be gaps or no light, this would be destructive interference. So there's a lot of support, a lot of evidence that, and that's why we call light a wave. We also see light reflect off of surfaces, just like waves. However, there's special circumstances where light doesn't behave like a wave, oddly enough, as well as other forms of radiation. So oddly enough, we have another theory of what light actually is called particle theory. This also goes with other forms of radiation as well, not just visible light. So what particle theory says is that light exists as the movement of particles called photons. You can think of photons as being like little bundles of energy. So light exists as the movement of particles called photons. Now I don't have a demo here for this one, a little too elaborate of a setup here, but a common observation that we have in which light does not behave like a wave is what's called the photoelectric effect. And this phenomenon is one that has a lot of physicists kind of scratching their heads because how can light behave like both? Why does light not behave like a wave in this situation? So what a photoelectric effect is, or what kind of happens, the gist of it with the photoelectric effect. So whenever we have a form of radiation, again, we'll just stick with light here, that strikes a metal surface, depending on the composition of the metal or the strength of the light waves, what we would expect to see happen if light was always a wave and always acted like a wave is that the waves would hit the beam of light and then the waves would reflect off. Instead, what we observe is that as the waves hit the metal, the wave is absorbed by the metal, and then the matter that makes up the metal actually emits electrons. So instead of emitting a wave, or instead of having the wave bouncing off, it just specifically releases, lets go of those electrons, those negative particles. So it comes in as a wave, but then leaves as a particle. So there are some scientists that say light is actually not a wave. Light is actually a beam of particles that can strike a surface and reflect off. Now, since we have multiple observations in which light behaves like particles, and we have observations in which light behaves like a wave, most scientists have accepted what's called the wave-particle duality theory. So what wave-particle duality theory says is that light exists and behaves as both a particle and a wave. So it is simultaneously the same, or simultaneously exists as both a wave and a particle. Or you could think of it as when light wants to behave like a wave in certain circumstances, it will, and when it wants to behave like a particle in other circumstances, then it will. We don't know why it exists as both a particle and a wave, or why it behaves like both a particle and a wave, but since we can't figure out, science is an observational field, so if it looks like both and behaves like both, until we can figure out otherwise, it must be both, right? So wave-particle duality theory is currently just the accepted theory as to what light actually is. It's actually just both a particle and a wave because it acts like both of them. So because it acts like both a particle and a wave, there's tons of different phenomenon that happens every day because of visible light. We're just going to focus on one over these next few days. We'll look at others, of course, later on in the upcoming weeks. And so this is going to be the section of our notes where we're going to start looking at the law of reflection. So the law of reflection we can use to predict how light is going to behave when it strikes a flat surface, a flat reflecting surface. So what the law of reflection says is that when light, and again, you can technically apply this to any form of electromagnetic radiation, but when light hits a flat reflecting surface, the angle of incidence will be equal to the angle of reflection. So when light hits a flat reflecting surface, the angle of incidence will be equal to the angle of reflection. So what exactly does that look like? So we'll have a drawing we're going to do and a few words we're going to define here. So for our drawing, let's draw a mirror. So just some flat reflecting surface there. Hello. We're going to go ahead and draw one of these on our sheets of paper. Now we want it as straight as possible here, so why don't we just go ahead and follow one of these lines. So we'll draw a straight line here, and we'll label that the mirror. Now in order to analyze the law of reflection a little bit easier, we're going to draw a dashed line that is perpendicular to the mirror surface. So we're going to grab one of our protractors now. So everybody take a second to grab one of those just so we have as perpendicular of a line as possible. So if it's been a while since you've used a protractor, so this circle is going to be kind of our leveling line. So next to this circle, I have two lines that are horizontal here. So I want those horizontal lines to go flat right over top that mirror line that I drew. And then perpendicular is 90 degrees. So I'm going to look up here and find 90, and then 90 is just straight down from here. So I can just draw like a little dot here and maybe extend that down over here. And then this is actually a straight edge, so double nice. You can flip this around, line up those two dots with my mirror here. And this line that I'm going to make as a dashed line. There we go. Froze for a second. And label this here as the normal. A little box here, show this is a 90-degree angle. Now let me take a second to define this term here. So what our normal line is, this is a dashed line that is perpendicular to the mirror surface. And what this is going to be is my reference line. So my reference line to my light ray before and after it strikes the mirror. So now when I go to shine, a light ray onto a mirror here, I have a beam of light that approaches the mirror, and then I have a beam of light that exits and that leaves the mirror. So the light ray approaches the mirror, it hits the mirror, and then it reflects or bounces off the mirror. So the ray before it hits the mirror has a special name, and the ray that leaves and that reflects, that bounces off the mirror has a special name. So we call the ray that approaches the mirror the incident ray. And this is the ray of light. Heading towards the mirror. So ray of light that is heading towards the mirror is my incident ray. Now, the ray that's going to bounce off and reflect or reflect off is what we call the reflected ray. This is the ray of light heading away from the mirror. So reflected ray, ray of light heading away from the mirror. So let's use our protractor to draw an incident ray at a particular angle here. So let's keep it nice and easy and say 45 degrees. So when I go to use my protractor to draw out these light rays, we're going to practice this now because you're going to be doing this over the next few days here. So I have my normal line that is vertical. I'm going to line that up with the vertical line over here in the center diagram. This is like my centering leveling line here. So I'm going to line this vertical line up with the line coming from that dot. And then I'm going to line these horizontal lines with my mirror surface there so that I am nice and centered and leveled here. All right, so any angle that is less than 90, if you notice up at the top, I have those that are listed. Once we get to 90, on this side it gets bigger all the way down to 180. And then on the inside, if I was going the opposite way, then I have those larger angles. And then over here, I have those smaller angles. So we're going to draw an incident ray that is approaching the mirror, let's say at 45 degrees. So here's 40. This goes in increment of 1. So here's 40. Here's the 1, 2, 3, 4, the 5. So if you want, you can kind of eye out, since your protractor might be extending off the paper like mine. You can just kind of draw a little line, eye out, down about where is it at 45 below. We'll just put a little dot there. And I can take the straight edge on my protractor, line that dot up with the normal. So the normal is going to be the dividing line at the location where that incident ray strikes the mirror. So it's perpendicular 90 degrees to where it strikes the mirror surface. So I'm going to draw a line from that dot that I marked to my normal line. And then I'm going to draw an arrowhead to show that this is the light ray that is approaching, heading towards the mirror. And here we can label it too. We'll give that a label of incident ray. Now this is going to hit the mirror and reflect, bounce off. Now the law of reflection says that the angle of incidence is equal to the angle of reflection. So now the angle of incidence, what that is the angle that is made between the normal and the incident ray. So this angle here is the angle of incidence. So since we're doing 45 degrees, so halfway from 0 to 90, in this particular drawing, my angle of incidence is 45 degrees. And you can put a little note down here, define this term, angle of incidence. This is the angle between the incident ray and the normal. So angle between the incident ray and the normal. So the law of reflection says that the angle that this reflects off is going to be equal to the angle of incidence. So if this strikes the mirror 45 degrees from the normal, then it's going to reflect at an angle of 45 degrees from the normal. So I'm going to take my protractor here. I'll line it up again. So I want the horizontal lines flat on the mirror surface. And then those two black vertical lines lined up with my normal. I can check to make sure that this is lined up with 45. Okay. So now I can go through here and find 45 degrees. Extend my dot down. And then line it up from where we're at with the normal line up to the top. Connect those two there. Oh, I ended up being, oops, off a little bit. I didn't quite get that on the normal line there, did I? There we go, it's a little better. And then it reflects, so it's heading away from the mirror. So you can draw an arrow going back out. So it comes in, bounces off. And so this is our reflected ray. So this angle between the normal and the reflected ray is known as the angle of reflection. So if this hits the mirror at 45 degrees, then it's also reflecting at 45 degrees. So I got one more vocab word, a little straggler that couldn't make it on this page here. So I'm going to go ahead and flip my page. If we need to pause the video, there's still people writing real quick, then that's fine. But if not, then here we go. So then that angle of reflection. That's the angle between the reflected ray and the normal. So the angle between the reflected ray and the normal. All right, so we're going to do one more kind of walkthrough, one more drawing here with our protractor here, because again, for some of us, it's been a while since we've used them, and just to get a little more practice here with the law of reflection. So for our problem, let's say we have an incident ray strikes a mirror surface. (20 degrees from the normal. Find and draw the reflected ray. So an incident ray strikes a mirror surface 20 degrees from the normal. Find and draw the reflected ray. We're going to include on here too, and the angle of reflection. So we're going to take a second to draw what this scenario would look like using our law of reflection. So first I need a flat mirror. Again, the law of reflection only works if the mirror is flat. We will look at what happens with reflection when we have mirrors that are curved surfaces. So as you can imagine, it's going to bend the line, and it's not going to be very even if it's curved, but we'll get to that when we get to that. The law of reflection, though, is only when we have a nice flat surface. So we're going to draw a nice flat mirror here. And I'm going to need a normal line that's going to divide my angle of incidence and angle of reflection. So that's going to be the point where the light ray is going to end up striking the mirror. So again, we want to line up these black lines that are horizontal with that horizontal line we just did for the mirror. And then when that looks pretty level here, Here's 90, so we can draw a couple reference lines there just to make sure it's going to be a nice big straight line. Flip our protractor around. Line it up here. We'll do some dash lines to our mirror surface. So this is our normal. It's perpendicular, so at a 90-degree angle here. All right. So it says that it strikes a mirror surface 20 degrees from the normal. So one thing I always want to read is, what is the angle measured from? Is it 20 degrees from the mirror surface? So am I going up from here to here? Or is it 20 degrees from the normal, going here to here? So this is from the normal. So I'm going to start at my normal line, and I'm going to count 20 degrees over. All right, so I'm lined up here with 90. I got the vertical line lined up with my normal and the horizontal line backed up, lined back up with the mirror. And so it's striking 20 degrees from the normal. So I'm going to start at the normal, and I'm going to count 20 over. So 10, 20 degrees. I'll put a little mark here. Now, if you want, so while you have your protractor here, we know the angle of incidence is going to be equal to the angle of reflection. So if it's 20 degrees from the normal before it hits, it's going to be 20 after the 20 from the normal after it hits. So I could also kind of draw my reflected guidelines now here if I want, just to save myself some time. So it's going to start at 90, and it's 10, 20. I'm over here. So again, I'm measuring 20 from the normal, so that's why I'm counting over this way and over this way, because the normal is my reference line. So if it said it was 20 degrees from the mirror, then I would start down here and go up. And here's where I would land on 20 degrees, like we would presumably think of maybe when we first hear this problem. You know, generally, if you see 20 degrees, the first instinct is to look for where's 20 and there goes my marks, but we want to see what is it relative to. All right, so now I can draw my lines. I can draw my angles. So I can line up this line here with the normal and draw a straight line from there to there, draw an arrow. And I can label this as being 20 degrees. And this is my incident ray. And it's going to hit the mirror and reflect and bounce off. So I can twist my ruler around here, line it up with the normal and that line I made up at the top there. Make a nice straight line, connect those. Put an arrow there, and I can label that here as being 20 degrees. And if I look at them, you know, we're people, so it might be off slightly, but relatively they should be equal visibly when we look at it. So like if your incident ray is only from here to here from the normal, and then you go to draw your reflected ray and it's all the way like out here, you can visibly tell those two aren't equal. So that's kind of a nice way to check yourself before moving on to the next problem. So what you're going to get now, you're going to hold on to these protractors for a moment. So you're going to get now a practice. And so here's a reference for you of the law of reflection. We're going to use the law to either find the missing values of the angle. You know, for this one here, for example, we know this is 90. If this side's 30, then this side is 30. So we can use subtraction 90 minus 30 to figure out, you know, what these guys are. So use your law, use subtraction if needed to figure out what any of these missing angles are in the picture. And we have a couple drawings that we're going to do, so you'll use your protractor for that. And then just a couple multiple choice questions that we have. So in a minute, this assignment's going to get handed out. You're going to work on this independently, so on your own here. And then when you're done, I have a video, another video that's posted in Google Classroom that has the key to this. So, you know, hey, what's the answers? And here's why they're the answers. So when you're done with this assignment, I'd like you to, at your leisure, since everybody's going to be getting done at different times, to find that video, watch it, compare your answers to what's on the video. So then that way when I see you all on Monday or Tuesday next week, we can get any questions answered right out of the way that couldn't be answered with the video before we move on with things. So you can watch it in class here, you know, on low, on your cell phone or on your headphones. If you end up watching it later, once you have this done, then that's also perfectly fine. This though just needs to get done here within the block hour, which you have plenty of time to do. When you're done, you're going to bring this assignment up to the sub, so show them that you have this done. Again, sub, thank you for being here today. You're going to return your protractor, so you don't get to keep it, unfortunately, so make sure that gets brought up too when you show them that this is done. And then once you have this done, the substitute is going to hand to you the assignment that you're going to do for the second part of the block. And so I have a computer lab for you. So those Chromebook carts are in the back. Make sure you plug them in when you're done with them. But there's some websites that you're going to go to, and you're going to play around with the law of reflection, and it's going to be an introduction to mirrors. Main focus is mirrors here. So how does the law of reflection apply to mirrors and the images that you see in particular mirrors? If you don't want to look up the links, or I'm sorry, if you don't want to type up the links, I do have the links posted in Google Classroom as well. So after you watch this video in Google Classroom, you can open up those links in Google Classroom, so that way you don't need to manually type them all in. I will be just an email away for any questions if we happen to have any questions, but otherwise, hope you all have a nice day. Make sure that we're bringing back those protractors and that we check our reflection practice once we get our sheet and we have that all done. Any questions, just shoot me an email. I'm just sitting in an office right now doing some curriculum writing with some people, so I'll be able to get questions fairly quickly. Have a good day, and I will see you all next week.